Okay, so that proof, it proves the result, but I don't think it leads to very much understanding of the result. So I think that this is worth looking at an example. And the example that I would like to do, let's start with something that we know. We know that the Laplace transform of the sine of t is equal to 1 divided by s squared plus 1. And so what I'd like to do is use this periodic function Laplace transform formula to find the Laplace transform of the sine of t. Let's just make sure that it works out. And before I get started, let me just tell you, this is a terrible idea. Deriving the formula for the sine by using this periodic function is going to be tremendously more work than what we were doing before. But we know what the answer is, so this will kind of give us at least a frame of reference to see that this does in fact work. So if I want to use this to find the Laplace transform of the sine of t, I'm going to take advantage of the fact that capital T is equal to 2 pi, and f of t is going to be the sine of t. So we'll keep that as our answer. And now I'm going to try to use this formula to find the Laplace transform of the sine of t. So the formula says that it's 1 over 1 minus e to the negative 2 pi s times the integral from 0 up to 2 pi of e to the negative st times the sine of t dt. Get a little more space here. I am going to use the table of integrals to evaluate this integral. So this will be 1 divided by 1 minus e to the negative 2 pi s. And then the integral, let me look at my integral table. The integral is going to be e to the negative st divided by s squared plus 1 squared times negative s times the sine of t minus 1 times the cosine of t, all evaluated from 0 up to 2 pi. So we need to evaluate this from 0 up to 2 pi, and because the variable here is t, the s squared plus 1 is a constant. So I'm going to bring that out. So this will be 1 minus e to the negative 2 pi s times s squared plus 1. Those don't have t's in them. So then I'm evaluating the e to the negative st times the negative sine of t minus cosine of t. All right, so if I evaluate that at 2 pi, I will get e to the negative 2 pi s times the sine of 2 pi is 0, the cosine of 2 pi is 1, and then I subtract what I get when I evaluate 0, so that is going to be e to the 0, which is 1, times the sine of 0, which is 0, and the cosine of 0, which is 1, so minus 1. And all of this in here is going to be, looks like I have positive 1 minus e to the negative 2 pi s. So all of that cleans up to 1 minus e to the negative 2 pi s divided by 1 minus e to the negative 2 pi s times s squared plus 1, and those two things cancel, and I end up with 1 over s squared plus 1. Let me just say again that this is a terrible idea. If you have to derive the formula for the Laplace transform of the sine of t, don't use this formula, but you can see that this formula does in fact work. When it comes to the types of problems that we really do care about with regards to this formula, I go back to my previous example, that if I had had f of t, and we were looking at 1, 2, 3, 4, and it was this sawtooth pattern where it looked like this, then I could look at integrating just over that interval of t, and this formula would end up being a really, really nice way of doing it.